My name is Shanfeng Shao from Beijing Academy of Quantum Information Sciences. It's my honor to have the opportunity to present our recent work. The title is High Key Rate Intercity Quantum Key Distribution Without Optical Reference Light. So before jumping to the details, I'd like to introduce the background and our motivation. Proposed in 2018, twin field quantum key distribution improved the key rate scaling from O eta to O square eta, surpassed the replace bound based on the single fault interference, but the strict global phase requirement at the system complexity. To perform the TFQPD, the laser frequency synchronization was required. The common method includes ultra-stable laser with calibration and the frequency determination. Besides, the strong reference light is required for the compensation of phase drift in the long fiber and the residual drift of the lasers. These factors increase the complexity of system, especially for multi-user network. While TFQED performs well over the long distance, such as the 800 and 1,000 kilometer experiment, a similar solution for the metropolitan and medium range intercity network is required. Recently, Sequence MDI, also called modern pairing QPD, was proposed by Yin and Mar, while preserving the measurement device security and the key rate loss scaling. This protocol eliminating the need of phase locking, thereby decrease the requirement of system, making them a promising solution for the high key rate quantum network. In contrast to the MDI, AMDI enables the post-measurement pairing as long as the interval between the response events is less than the threshold. So if the threshold is sufficiently long, the probability of the pairing reaches to 100%. Consequently, the pairing generation rate is proportional to the single arm transmittance, and so does the secret key rate. These days, the experiment of the model pairing and the AMDI was achieved. The first work used the compact laser, which is easy to integrate, but the key rate remains to be improved. The second work using the achieve the high key rate by utilizing the ultra stable laser, but is limited by the bulky, heavy and expensive setup. So a simplified system to achieve a high key rate is essential for the quantum network, and it is also the goal of our work. Besides, we also noticed that for the coherent protocol, such as TF and AMDI QED, the megahertz level reference light is always required, which not only introduce the additional noise, but also increase the requirement of the high counter rate detectors. Besides, in the case of APD, the after pulse effects should also be considered. To mitigate these issues, dual band stabilization was mentioned, which will introduce additional device and resources. Moreover, the time multiplex the ref light reduces the duty cycle and imposes additional burden on modulation searching. So limiting the reference light is benefit for the simplifying the system and its performance. So let me introduce our experiment. This is our experimental setup, which follows an open channel structure. Each user was equipped with a compact laser whose drift rate is about 15 megahertz per day. Besides, compared to our previous work, we upgrade the encoder. The clock rate was upgraded to 2.5 gigahertz, and all the modulators were enclosed in a box with active temperature control. However, due to the fast drift of the compact laser, AMDI could not be directly performed. The left figure shows how the X-Cuber varies with the frequency of sight at different distance. As the figure shows, if the frequency of sight exceed megahertz level, several megahertz, the AMDI could be impractical. So frequency estimation is needed here. Fortunately, we were inspired by the asynchronous pairing from our former AMDI work. We noticed that firstly, the frequency of sight could be extracted based on the correlation between the error rate and the pairing interval. The second, incorporating the recycled pairing allows for the extraction of additional information. And the third, the announced decoy state is suitable for estimation. So we combine the three ideas to develop our method. In our experiment, the frequency estimation was performed by recycling pairing the announced decoy state. We extracted and accumulated all the pairing with the phase differences of 0 and pi. Calculating the X-Cuber and record the interval at the same time to get the right figure. This figure clearly shows the information of frequency of sight, indicating 11.80 megahertz. The frequency of sight is extracted by performing the FFT on this curve. So using this method, we could make a combination between the frequency of sight estimated by using our method and using an optical to electronic converter at the same time. This figure clearly shows that we could accurately estimate the frequency of sight. So use the result, we could make a compensation of phase. After the compensation, the X-Cuber decreased from 50% to 29%, which is about 3% lower than the former works. So our method do not need Refe light, allowing 100% dual cycle, and our method requires low counter rate about 10 kilohertz, 100 times lower than before, suitable for APD and low counter rate SNSPD. However, in practice, the rapid fluctuation in the fiber and the lasers cause the damping, making the curve convert to 0.5 at a large pairing interval, which lowers SNR of estimation. So the maximal pairing interval for estimation is set as 100 microsecond and 10 microsecond in 100 and 201 kilometer experiment, means 10 kilohertz and 100 kilohertz resolution. This resolution could be improved by using the padding zero method. Another thing we have to discuss is the security. We point out that compared to the original AMDI, our method do not introduce any additional security problem. The reason is summarized at two main points. The first, the estimation process is independent of coincidence pairing and does not affect it. The second, it requires no information beyond the standard reconciliation information, and the message exchange between the X and Bob remains unchanged from the standard AMDI. So after discussing the method and the security, we compare our work with the related work. As the table shows, while simplifying the system, we also achieve a significantly high key rate, 1 order of magnitude improve over the works using compact laser. Our search may achieve a similar complexity as MDI QPD and increase the key rate by 2 order of magnitude. Even compared with the highest key rate experiment, our performance remains comparable. So our work paves the way for cost-effective, high-performance quantum network. Furthermore, we utilize the ultra stabilizer to perform the higher key rate and the longer distance. A comparison with the other state-of-art work is shown in the figure. As a result, we achieve over 1 megabit per second secret key rate at 100 kilometer while providing measurement device security. And we also set a new QAD record for 200 to 400 kilometer distance range. So in a conclusion, our method requires 100 times fewer count rate than the previous search method, limiting reference light and enable 100 kilometer, but 100 percentage quantum dual cycle, and we making a significant advancement of over 1 order of magnitude compared to the work using compact laser, and we also achieve a record key rates in 200 to 400 kilometer and exceed 1 megabit per second MDI QAD at 100 kilometer with ultra stable laser. And around the same time, Professor Pan and Professor Xu achieved a modern pairing QAD with compact laser, and both of the two works make the AMD and mono pairing more practical and efficient. Finally, we present an outlook of our search mate. The key limitation of extending to the longer distance is the low intensity of our decoy state. So we could use the optical frequency comp to achieve a longer distance by offer the dual bands technology with 100% dual cycle. And we could also adopting a 4 intensity search mate to generate stronger decoy states. To increase the pairing number further, we also could use the phase slices near 0 and pi. Another thing is the resolution. We could use the padding 0 to increase the estimation resolution. Enables a frequency resolution better than 100 Hertz, which is sufficient for 500 kilometer experiment. Finally, we sincerely thanks every author for their support, especially for Professor Yuan, Professor Yin, and Professor Zhou. Thank you for your attention.
Thank you for the nice talk. Time for some questions.
Thank you for the interesting talk. I have a question about security analysis. Do I understand correctly that you said that it's the same as with MDI? So you have you use a mode pairing QKD, but there are papers. So security analysis of mode pairing QKD is non-trivial because pairing pairs are not fixed. So entanglement-based formulation is a priori not obvious. Of course, there are papers resolving it, and also there are, I don't remember the details, but I saw papers about finite key analysis for mode pairing QKD. So I think there are differences with the usual MDI.
Yeah, our method achieved a similar security as the original AMDI.
But do you know these papers about finite key analysis for mode pairing QKD?
I know, but I'm not expert at the theoretical about
Okay,
the.
Okay, yes, please. I simply want to draw your attention. So there are some papers precisely about finite key analysis for mode pairing. So there are. I also don't remember the details, but could be some differences with the usual MDI. So it's there are known results in it.
Okay, I will take attention about this issue.
Do we have more questions? Yes, one over there.
Thanks for the nice presentation. So you mentioned about frequency compensation or estimation. May I know how do you do the compensation at the end, and how fast did you, what is your compensation rate?
Because our method, because AMDI is more robust for the frequency drift, so we could have a longer time to accumulate the pairing information in the 100 kilometer experiment. We compensate the frequency at every 0.2 seconds, and for the 200 kilometer, we compensate it every 10 seconds. 10 seconds. So what we are next do is to increase the intensity to achieve a longer distance, because in the longer distance, the pairing interval is more longer. So we have to compensate it at a faster speed.
Thanks. I have one more question. So in your distance, do you consider a symmetric case or asymmetric setting between Alice and Charlie and Bob and Charlie? Is it a symmetric or asymmetric distance?
Okay.
Yeah.
In our method, we achieve the symmetry channel.
Okay. Do we have more questions?
Okay, and thank you for a nice talk. I want to know in schema, how does polarization feedback? You need a polarization feedback?
In our experiment, we use the EPC at the standard set. Standing set.
What is rate?
About 10 of hertz.
Okay, thank you.
Okay, I think maybe it's time to move on to the next talk. So let's thank the speaker again.